and I've labeled them. OCPD, remember that just means breaker or also, which we don't do much of really, talking about it. Maybe we'll talk more about it next week, but fuses, selecting fuses. You'll get into that conversation more so, and more centered around better, which those who've worked with motors will know. Fuses are more likely to be found in the motor world than residential or commercial stuff, but they do find their way in. 31016 for wire selection, and then this is the one we looked at yesterday with the temperature correction factor. That's what CF means if you need to write that out. Actually, this one's not labeled, although table 8, that's what it is, but this one is the circular mills. And we need that one for voltage drop. That's for the voltage drop formula. All right, so you can tab these out, get them ready for usage tomorrow. All right, I think that is almost everyone. Okay, so let's jump into everything. Let me pull up the, oh, I have the code book already open. I'm literally looking at it. I was about to open it. So here's the first thing, and here's how I like to start all the reviews, which is, let me go back one just to address it here. These are the 3 articles that we are looking at for exam 1. Just like when you open up the Mike Holt workbook, this is why it's important to do that assignment. You just get these random questions about a bunch of different code sections. So questions like how Mike Holt structures them are free game from any of the 3 articles. All right, I will have you go source a question out or an article out that has a specific, just around the way that Mike Holt sets it up. So keep that in mind. Anything out of that's why I said bring your code book in, because there might just be a simple, what is the blank for a branch circuit in a bathroom or something like that. Just something you have to go directly. There's no note for it. It's no math equation or anything. It's just walk over to the actual code section and then find the answer. So within Article 210, 215, and 330 out of the MC world, like I said, any question or any article is free game as a question. Now, I try to center 95% of all the questions that I ask around stuff that we've covered. But again, because it's going to help you in the future as well, just like, again, doing the Mike Holt workbook, it's just here's a random article, go find this, and again, troubleshoot it and learn to navigate through the code book, which is how questions are going to come at you for those, again, going into the journeyman stuff. So here's Article 210, all right, and this is all of the notes centered around all of the math that we're going to have to do, all right? Aside from standard code questions, where, like I said, you might have to go find a height to something, or how far do these outlets got to be, all of that. These are the math notes, all right? These are the math notes. Now, you have all of these, but like I said, if you want to coordinate all this today on one sheet, so you just have this one sheet tomorrow, good to go. But today, as we start to do now our review, I'm just going to ask a bunch of questions out of each one of these. So we'll select an overcurrent protection device. We'll do the general lighting, find the breaker situation. That's the green square. All right, we'll do voltage drop using the circular mills. There's the K factor. Whoops, sorry about that. I had the move thing. There's the K factor there as well for copper and aluminum, which again, I don't ask a lot of aluminum questions, but have the information because I change every exam, and so I'm always having to reframe a question, so I'll use aluminum or copper. I'll vary between aluminum and copper. And then again, what we did yesterday with the temperature correction factor.
Will the journeyman exam have you like do calculations on pipe bends and like stuff like this? Like,
Mm, yes, yeah. You'll get standard 90s and offset questions on a journeyman exam. Actually, wait a minute. So I've taken other tests in companies, and they've obviously a company trying to hire you would ask that, but now I'm confusing it. I think that the journeyman exam is everything out of the code book, which the code book does not have anything on conduit bending, other than to make them nicely.
but I'll have stuff like this, right?
This, yes, this is not, yeah, absolutely. This 100%. From definitions, you'll get a couple of definitions. There'll be questions as easy as that. Which one of these is a definition of a branch circuit? And you'll have a multiple choice to choose from. But they write them very sophisticated. You'll look at all four of them; they all look like they could be. So you literally have to go to the code section and find it. And then like everything really that we go over is usually what I've taught at 3 schools, and all the curriculums are set up around the journeyman exam. And so all of the articles that we focus on are the highest percentage articles that show up on the journeyman exams.
We can't find any like practice tests online.
I'm sure you could, but you have a practice test, even though it doesn't seem like one, with the Mike Holt book. Mike Holt uses former questions asked on journeyman exams. But I'm sure you can find them. You can find practice ones. Now, also, don't forget we have a supercomputer, so you can have ChatGPT ask you sample questions, and you can just give it articles. All right. So, but I would say there you try to focus it around California, and it'll try to find as much data as it can, which is what we do as schools too. Try to find as much data as we can. This is again what Mike Holt does. Try to find as much data as they can and just use that information.
So your curriculum is based on ChatGPT, is what you're telling us?
What's that? The what now?
Your curriculum's based on ChatGPT, is what you're telling us?
I mean, ChatGPT knows everything, so everyone's curriculum is based off of something ChatGPT can pull up. But no, this curriculum was given to me, so.
I got some questions wrong.
No, also, I write my questions, so try to put them in a computer. It's not going to understand me.
Challenge accepted.
Yeah. Well, no, this is why, going back to new phones and tablets, that's what we're trying to avoid. This showed up after chat showed up. We didn't think about that.
I'm showing up in the Apple Vision Pro.
Yeah. Teachers did not know that the supercomputer was going to end up in the hands of students.
The giant. That's just my glasses, man.
But I'm all for it, we bring the code book on job sites. You bring Uglies books on job sites. If you have a better Uglies book, then use the better Uglies book. Why wouldn't you use the better Uglies book? Because it happens to be AI and we're trying to hate on it? I don't know. It's just another tool. In that world, obviously, if they become intelligent and take over the world, I don't want that. But as a tool, I think it's a very useful tool. And I think it's going to flow into, I don't want to get off topic, but here I have one of our PLCs back here. It'll involve itself in PLC programming too, but we'll have to learn how to use it there as well.
I think as far as like lighting layouts go, you can like take a picture and ask Chat. I think it's cool for that. Like, and you can show the client like, this is what it'll look.
Sure. Yeah, absolutely.
And lights in your ceiling. Yeah.
Yeah. It's as a tool. I think it's a great tool. I think all tools have been good tools that we've modified into the electrical world. Okay, let's start these in order of. Well, I guess we'll just start them in order of the way we find them here. No real reason not to. So the first one is the OCPD selection. Remember, just because we actually, it shows up to point this one out, which I don't have it here. Why don't I have it here? Over here when we get into conductor selection. So, in fact, I have to add one here. I am literally missing an article that we need. So, apologize, but there's a spot for it right there, which is 210-19. Sorry, OCPD selection I have there, but conductor
I messed up my organization.
selection, I apologize for that. You put it in order? That is quite annoying.
Now it doesn't look.
But yeah, we need that one, which is based off of the same thing. They're both going to go in the same direction as far as using the 125. And the CON, hopefully you understood that that meant continuous. Minimize even more. So we'll need that one as well. Or that'll be another article that math will be coming out of. The article. So let's do a couple of examples. We'll do them both at the same time. All right, we'll knock out 210-20 using 240.6 over current protection selection. 210-19 using, which we don't have it here, which I'm going to give us as a set of notes next, Article 310-16, but you can already write that down if you want, alongside, I'll go back one, to that one that you wrote here, if you wanted to. All right, now we'll take a page and we'll field some questions. And they're both going to start off the same. I don't really try to get too fancy with the questions, like set up different scenarios. Questions get harder once we find these next questions again in the final, but in the beginning, it's just straightforward. I'm just looking to see if you know how to use the tables correctly and know how to do the math correctly to find the size of a wire or breaker. So conductor would be one question. What size conductor is needed for, and let's do them both at the same time so we can just remember how to do them. Continuous load, which numbers will change for the questions that you'll find on the exam. Ampere and non-continuous of non-continuous of, and here again we'll have a different load there. So in fact, let's just do them, like I said, as I was writing this, I feel that we can, let's just do them both at the same time. Let's find, as if we were actually setting up a circuit for somebody. Let's find the wire and let's find the breaker that we're going to use for this circuit. It's the same, and this will knock out 4 questions overall. How to find a continuous load breaker situation, how to deal with a non-continuous load situation, and then the same thing for wires. All right, so we get to knock out a couple of questions just there. So what changes are the numbers? So let's put a couple of numbers here to work with. Anything will do. Sometimes I want to make sure they land on a specific number. So let's go with some large loads that we're dealing with, 56 amps, and a non-continuous one of 45 amps. Now again, we're looking for one breaker and one conductor for both of them. And then wire. All right, take your time. Use your notes. There's one giant note we need, which addresses the percentage that we're applying to one of these specifically. It's the one giant note you need for wire selecting and breaker selection. Don't forget the 125 for continuous. From there, the 2 tables, which I'll also add here.
A lot of page turning going on in here. You may want to show us how to do it.
That's why I'm letting when I hear the pages stop, that has been my cue the whole time. It's funny you mentioned that. That's all I've been listening for. I was gonna wait for the pages to stop, either assume that we didn't know how to do it, or somebody's got the answer. So good, if you're cueing me on that, then I will walk you guys through the process. All right, so 125% is applied only to the continuous load. So that means only the 50. Oh, by the way, I'm also recording this, so you'll have this if you want to rewatch it later. So much that I do. No, that we're supposed to do. So there's my first step in adjusting the 1 amperage that needs to be adjusted. Again, continuous load operates for more than 3 hours or 3 hours or more. And so because of that, we try not to put the breaker or the wire too close to the 56 amps. Because if you get into these 8 hours, 10 hours, 12 hours of operation, this can start to really weigh on the wire and the breakers. Breakers can start tripping. So we increase it, and this will give us 70 amps. You see, we've got a nice 14 amp buffer now that we've set up for the breaker and the wire. Now, to non-continuous loads, none of that has to be done, so we don't do anything. But we do, since we're going to find 1 wire for both and 1 breaker for both, do have to add this up. All right, so I'll pause right there, let everybody kind of get caught up. So far, if there's a number that you're looking at that you don't know why it's up there, let me know.
Does that move it into the 75-degree column?
Very good. So we're already getting there. So we add these two up, 45, and this will give me 115. So we're looking for the wire first, I'm assuming, just because we're asking about the column, which is good because I have that column right here, or that table right here. So yes, because we have 115, this places us now in the 75-degree column. Very good. So you can see the wire number 2.
Those again. Okay, just no mistakes.
All right, number.
And you'd have to use a 125 amp breaker.
Right, so now the breaker, they don't make a 115. So here again, let me just remind you, don't let this is where multiple choice can fail you. Sometimes nice, sometimes not nice. If I put 110 or even 100, okay, you might. But if I start doing this, 115 might seem like a breaker, 120 might seem like a breaker. But we have to jump all the way from 115 to 125 because that is the actual one they make. They don't make this at all. They don't make this one. They actually do make a 110, which might not even seem like a breaker. 110. There's a 100. Why would there be a 110? There is. There's the only one that's 10 amps more than the next one. Well, in the hundreds, I mean. The small ones, of course, there's 10 and 15 and 20, but In the 100s, the 200s, there's no 210, there's no 310, there's no jump over a 10 in the big numbers like that. But and I don't even know why it's there. I think it might have to do with motors or specific loads. But here we are. All right, let me just get rid of some of that. We don't need this. So yes, 125 now is our main breaker. All right, for those who struggled with this, now let's re-ask this question in another direction, which is simply find me a breaker for each of them and a wire for each of them. So find me a breaker for a continuous load of 56 amps. Find me a breaker for a non-continuous load of 45 amps. Because those will be questions as well, not combinations, just the single one now. So you have to know how to deal with a non-continuous load by itself and a continuous load by itself. And now same thing for the wire. All right, so now we're looking for two. Continuous. Well, how do I want to write this out? I guess we'll put wire here, continuous wire, and continuous breaker. And then we have the non-continuous wire and non-continuous breaker. All right, let's see if we have page turning. Keep an ear out for the page turning.
What?
I'll be focused on it.
Yeah, that makes it sound like an idiot. Congratulations.
You can't see it, you can't see it, so you can see it.
Right.
All right, now I will ask for the continuous loads wire. Does anyone have the continuous loads wire?
4.
Number 4. Number 4. I'm going to say that is exactly correct.
They're under 100 amps each, right? So
There we go, the 60-degree column. Now, very good. Which, just to put it up here, the math we did was times 1.25. We did it earlier, which was 70. But now, don't. This when you get it when you're in these smaller amperages, sometimes like this, if you would have just simply messed up and gone to the 75 column, you would have landed on the same wire. Because the differences between the amperage on that one, 60 and 70, is not 85 is not too much. But when you start to get into the larger numbers, then it could be a significant amount that you start to jump across. You know, if you start to look at like the 900, it goes from 435 all the way up to 520. So that's a large gap now between those two numbers, where not knowing which one, obviously those are large examples of amperage. Okay. All right, so we got the number 4. Do we have the breaker on that one?
70 amperage.
70, right? They actually make one, so good. I think that was a hard to find at Home Depot or something like that. Now for non-continuous, remember we don't have to do anything to this number. So this is, I mean, you want to call it the easier of the two, fine. You're going to the same tables. But for the wire, again, you're staying now in the 60-degree column, and you're using the 45 as the marker now. So number 6, right? And then here again for breaker. If you know the breaker, if you don't, multiple choice can throw you on a breaker question where you might not know or might not think that it's a breaker. Something like this.
If it's continuous load, you always add an extra 25%, whatever the number is.
Yeah, continuous load, multiply out the top by 1.25, which is 70. So what's the non-continuous OCPD? It's 45.
45, very good, yeah, 45. They actually make that breaker, which doesn't, in this case, it could also trip you up where you're like, nah, 45 doesn't seem like an actual breaker. I'm just gonna go with 50. One of those trick breaker questions, but now this time it actually is. So let's kind of wrap this up so that we know where we're at with all of this, right? So in Article 210.19 and Article 210.20, we get told how to deal with a continuous load or a non-continuous load. And here you can see the difference since we've dealt with the same loads. Right? If you're looking at a continuous load, then we have to increase that by 125. All continuous loads have to be increased by 125. Whether you're looking for the breaker or the size wire. And again, this comes from, I'll go back to where we got this from. This is why we have them here. And just to understand, that's what OCPD selection means between these two articles and what conductor selection means there out of Article 210.19. So another thing, just if you haven't yet or already, go and into those articles and highlight that information as well. So that you can reference it too if you need to reference it out of the article. But that's the article that basically explains that, how to deal with a continuous or a non-continuous load, either individually, each individually finding a breaker for them individually, or finding a wire for them individually, and then putting them together. All right. Now again, remember, there is a lecture that goes into all of this, posted. So you can watch that. Has questions there as well. And then if anyone needs more questions, all right, because I'm going to move on to the next thing now and do some more math with you guys. If anyone needs more questions when we're done on this one specifically, like the rest that we're going to do now, I got those, but this one I'm still struggling with, then after class hang out and we'll deal with now that one-on-one. And remember, I'm also recording this, so you'll have this for later. All right, let's move on to the next thing. Unless there's any questions here and now for this one that we can address before we move on. All right, good. Now let's go on to the next thing. And again, I'm just dealing with them in order. Now I did skip it as an order, but it is a little bit of math that we're going to look at. And it comes out of Article 210.11, which is branch circuit selection. And this is the article that gave us how to figure out how many branch circuits we need in a dwelling unit. Now, there's a few things that it tells us, like it says how many branch circuits we need for a what they call the small appliance circuit, or in the kitchen on the countertops. Small appliance circuit. It says I have to have 2 of them, and they have to be 20 amps. Laundry circuit, I need to have 1 of them, it has to be 20 amps. Bathroom, etc. It tells me all of these, but for our general purpose receptacles, or what they call general lighting, that's why I have it written as general lighting. Since it is a general light situation, they don't know what's going to be going in there. They give us a wattage per square foot or a VA per square foot. All right. This is the article that it comes from here, Article 210. Well, it starts there, and then we have A, number of branch circuits, and then B, where we get the reference to the VA per square foot. All right, or with a, again, load calculation based off of the VA per square foot. So let's do an example of that. All right, this allows us to also put a page here. Actually, wrong direction. There we go. This allows us to know how many breakers we're going to need. So that's how the question actually gets asked. The question gets asked by how many breakers are needed blank breakers, because there's 2 amperages there. Let's just put 15 here for now, but as a reminder that this can change for the exam. How many 15 amp breakers are needed for a square footage? I guess we don't need the A. All right, now, if I want it, I do put this in the exam, but I forgot to put it here. How many general lighting they're called. All right, as a reminder, general lighting is also receptacles. Let me clean up that lighting. Your general purpose receptacles and your lights in a dwelling unit. And they call them general lighting because way back when they first put electricity in houses, there was only lights that went in the houses. So it's just an old term that we've carried on forever. So, sorry, I left you guys blank there. Let's put a square footage here. 2,000 square feet. Again, it's represented like that. And so again, this is how the question gets asked for Article 21011 and the VA per square foot. So we have to remember, and I'll put them here, the things we have to remember are the 3 VA per square foot. We also have to remember Ohm's law, right? We have to remember Ohm's law. We have to divide by, and I'll put the number here, 120. That's the other number that you have to remember. You have to remember 3 VA per square foot, and you have to remember the 120. It is not found in the article, not in that article. The 121 comes from an article above 210.6 that says those outlets are going to be 120 volt max. All right, and we get to the amperage now, and then we divide that by breakers or breaker size. All right, here's the formula.
That's 6,000 divided by 120?
Correct.
Okay.
Correct. So yeah, I'll kind of get us started since it's just the first step, times 3 VA. And now we have that much wattage.
So current is 15.
Or, remember, this is
So
the P in the Ohm's law.
and divided by the size of the breakers, not like many breakers.
Now, who remembers the last note for this? When we get to the number that we find on our calculator, what do we have to do with that number?
Round it up.
Round it up. Very good. So I'll just plop that down here. Always round up. Because we are looking for physical items, so we have to complete the 0.3 of that item. So we have to buy a whole breaker for that 0.3. Alright, so if we complete this, and I'll set it up over here, Ohm's law, 6,000 divided by P over E equals I, then this is 50. So here again, if this was 20, we divide by 20. Keep that in mind. Always a reminder, it seems silly, but sometimes people just they look at their notes, they notice we wrote 15 somewhere. All right, sometimes people try to bring the equations that I wrote with them. That could get confusing sometimes because we've done different examples. So some might just use 15 because I saw it on my notes. If I put 20 there, we divide now by 20. because that's the size breaker we're going with. In this case, 15, which, like I said, we land at a 3.3, so we have to buy a fourth breaker for that. And then try to evenly distribute the amperage through those. How do we control the amperage on these? Since I don't know what a homeowner is going to plug in, well, same amount of outlets per breaker. Don't put like 8 outlets on one breaker and 3 on the other one. You're going to obviously, or not obviously, but potentially overload the one that you've put more outlets on. Which is another way to limit amperage on a circuit. Just limit the amount of outlets you have. All right, any questions on this one? This one doesn't require a table. There is, again, the code section that this comes from, which is what I've referenced here. That's the 21011 for general lighting, but there's the 3 VA per square foot divided by 120 note. Both notes are here.
No, I like this one.
Yeah, this one's straight. Good, because next week it follows us into Article 220. We do this one in a bigger scale, because this is only the beginning. This is only the general lighting part of the dwelling unit, and then from there we'll include all the other things that the house can potentially have and start to reduce this wattage by different percentages that the code book lets us do. It gets into a lot of fun math.
This is fun, man.
Yeah, right. This is I like this. This is enjoyable and very useful. You know, it's like anything. You have a friend wants to turn the garage into an apartment. All right, how many outlets do we need in here? How many breakers do I need? We apply all of these things to it. That just it's an area per square foot calculation, which you can do to any area, as long as it's a dwelling unit.
Is this what contractors use to figure out?
100%. Yep.
Okay.
When a house gets built, there is a higher percentage that the electrical company is just going to have to do the prints, the electrical blueprints on their own. All right. So, you know, because it's just less people involved. Like if you're building a Kmart, or who builds Kmarts anymore? If they build a Target, sorry, a Costco, I don't know, an Apple store. If you're building a place like that, then this gets hired. Engineers are doing this, architects. So here's where we get the blueprints and we just build to the blueprints. But if you're just doing a single home for somebody, then that, you know, cut costs wherever we can. The electrical company, you can just give me a set of prints and by the end of next week, you guys will have the blueprint for being able to calculate the service needed for an entire house or any area again that we can. Well, you have the area one now. This is it right here. This is how contractor would do it. This is how you could do it if you needed to wire up some general purpose outlets for somebody. Now, how do I wire up breakers for somebody if they're just not general purpose? What about the other ones? Here it is here. All right, we did the same thing, size breakers for somebody just buys a machine. I want to put this machine in my house. Or a friend owns a, I don't know, garage or a shop or something. I'm buying this thing. I'm going to wire it up. I had a friend of mine was taking some glass blowing, like making those glass things. The teacher needed to have these giant kilns put into a shop. Okay, how do you wire this up? He said, I've never seen these things before. Information, continuous load. These things are going to operate for many hours. Whatever the amperage on that machine says, continuous load increase 125, and then do this. Go find a breaker, set of wires. These are all very useful. This is also why the journeyman exams ask you a lot of questions like about this, because they know that you can do this on your own. They'll know that you'll be doing this on your own out in the field, and then they want to make sure that you know how to do that. All right, sorry about that. Just an email I got here. Okay, so let's go back over to here. All right, so this knocks out. If anyone, again, want to do any more questions on the square foot VA and find the breakers, we'll do them after if anyone needs any more examples. So knocked that one out, including that one and this one, and so now we're moving down to the voltage drop situation, which we have. Again, the K factor comes with the K there. All right, part of the formula. So now we also need the table. All right, and that table found on 725. Here's where we have the giant selection of circular mills. I'm gonna head over to that table just to have it here on my whiteboard. And so here now for this one, we're just now gonna use the assignment. All right, we'll knock out the assignment, or 77% of it. I don't know, there's 6 questions and we're doing 4. What's that percentage?
It's too much math. That's about it.
Sorry, I'm running down over to page 725 also, and here, and I'll pull up I have the example.
6.6 repeating, but
All right, remember this is this table here. The voltage drop formula, the one we're doing only requires the use of circular mills. So you just need that one circular mill section. And so let's look at a question. All right, let's look at question 1 here. All right, I'll put this one on the board, give you guys a chance to write it out, and then I'm going to head over to the whiteboard and set it up. Now, I have both the questions 1 and questions 2 here because they go together. All right, question 1 and question 2. Question 2 is a follow-up to question 1. All right, question 1 says I have a 240 volt single phase circuit. Now, the reason why 240 is there has nothing to do with the rest of this question. 240 is for question 2. That's the number that we're going to use when we divide by to find the percentage. But let's do question 1 first. So again, I'll hold here for a second and give everyone a chance to write this out.
that's a really good question.
Thank you. Thank you.
Is that number 6? Is he changing it then?
No, it should say number 8.
Oh, number 8.
Yeah, hold on. Let me zoom in there a little bit. And
Oh, there you
it
go.
more sorry, thank you. 1 second. Let me just square it in so that they're both available for you guys. And let me know if you don't see something.
We're gonna certify with.
All right. While you're writing, I'm going to be writing it up too, so then I'll have it here on the whiteboard for us. All right, now I'm going to just come over here, and there we go. All right, this is how we'll have the question, which again I guess I'll put the formula here. Voltage drops equal to 2 KIL divided by the circular motion. So that's what we have up top.
Are we assuming it's copper?
Yes, very good. Always assume copper, unless the question says otherwise.
But we don't have to assume because he wrote 12.9 up there.
Well, he didn't write 12.9.
Now, when you come back to this to do it later, I'll pop right back over to this, but I'll have it here as a note. Copper, all conductors are copper, which I forgot to show it earlier, but. And so for number 8, this number down here should be 6510. All right, I'll pause it here, leave it there, let everybody put this together. Again, if there's any number that you're looking at up here, specifically the green one that I have written out now, if you don't know why it's there, let me know. Alright, I'm gonna run this through my computer here. Divided by 165 Alright, so we should be looking at
10.938.
10.89, so we can call that 10.9, and we could live with 11 volts if we wanted. Now, usually the way I like to do a exam, just so there's no question as to stuff, it will exactly be that, or what you see, or I might just abbreviate to something like that. But I'll be very close as to what you're going to see on the calculator. Alright, but 11 volts, we can call that 11 volts. So now, go ahead.
So round it up, regardless.
Yeah. In reality, yes. This is 1189, or 0.80 is, or 0.8 and above is way close.
Okay.
My calculator is reading like 0.05 more than you guys.
Oh, you did it wrong.
Oh, really? A slight different.
I typed it in 3 times. It keeps coming out the same.
Yeah, mine says 0.89.
Mine says 0.94.
Mine says 10.938.
938. Look at that. So
Oh, yeah.
let's just live with 11. 11 sounds great to me.
10.94.
So we're gonna lose 11 volts. Going back over to the question 2. Question 2, and this is why we had the 240, the single phase 240, like a water heater or something like that. A phase, B phase, single phase. So now the easiest thing is, and I'll write it here as a formula because we don't have it here, but it's going to be voltage drop divided by E. So we just simply put 240 here. And this is how we solve question 2. Alright, this is how we'll solve question 2. So it'll be, you can do 11, you can do 10.9, doesn't really matter at that point. Now it's gonna end up as, and I'll just put it here for space, 0.045. Remember, this is a percentage, so we gotta move, whoops, the decimal 1 2 times. So this is gonna be 4.5%. That's what we're losing. We're losing 4.5% of the voltage in this circuit. Here's the formula for question 2, question 1, and question 2. So I'll pop back over here. Let's just pop back over for a second. Question 1, there's the 10.9, so question 1 is B. Alright, so this is what I would write down. Have this noted down, question 1B. So when you come back to this, you can select B.
So tell me.
And then question 2 says, what is the percentage voltage drop for the above question? And there, the 4.5 is what we came up with. Alright, so it'll be D, 4.5.
Can you go back to getting the answer again?
Yep, absolutely. So don't forget that question 1, B, question 2, D. All right, so here's how we got the answer. So let's fall back one. Question 1 said single phase, 250 feet away, 28 amps was the circuit. This was again for copper, unless otherwise mentioned. We go with that. And then the number 8, everything there turned out like that. And that means multiply, divide by, and again, we found the number 8. I'm just walking us through the whole thing, making sure everything is covered. The number 8, we found the 16,510 or 16,510 here. Sorry, hard to highlight sometimes with this one, but there's the number 8 there. Oops, sorry. This screen is now zoomed in, so I gotta correct it now for the code book. There we go. All right, so there's our number 8.
Yeah.
Okay. So then we divide, and we land at 10.9, or again, we said 11 is fine. There's where our question was answered there, and now we just divide. We apply this formula that's over here on this side. The answer divided by the voltage from the question. Which is how you find a percentage to something. How do I find the percentage of something? I divide that into, like, for example, if I have an exam and it's worth 100 points, but you got a 70, right? Obviously, this one's easy. I divide, but I can find the percentage to it by dividing. So here's how we find the percentage in voltage drop. Now remember, the code book gave us that 3% for a branch circuit. That came out of also Article 210.19 and in the feeders as well.
How does it change when it's a three-phase versus a?
Yeah, we can do a three-phase. I have one here as an example, just for fun. I think I have actually, not just for fun, the final exam, I have a three-phase question. But there's question 5. What's that?
Does the voltage drop even lower?
No, it all stays the same in principle of resistance and against versus the voltage. The only thing that changes is if I said this was,
Oh, using 1.732.
yeah, very good. If that was three-phase, then this would be 1.732 instead of 2. And this is a transformer related thing. The transformer that feeds a three-phase circuit versus the transformer that feeds single-phase circuits.
So 3 phases half a pi.
Is that what that is? It's the square root of 3, so that's the result of that. There's 3 individual transformers feeding it, so that's how we apply it. And, whoops, wrong way. And now we just do the math the same way. So you're not going to find this question on exam 1, but again, like I said, I put it as, that's why I'm letting you guys work on question 5 and 6 on your own, just because it's a little bit more interesting with the added 480 volts 3-phase to it. And for you now to find the percentage, then same thing, you just would divide now by whatever voltage I give you. If I say this is 208, then we divide by 208. If it's 480, we divide by 480. Let's do one more example of voltage drop. Since I was hearing questions and filling in as we were doing the process, let's do another one, which is question 3. All right, question 3 is another one just like this, not 3-phase, same question as is question 4. All right, let me know if you can't see. I'll try to zoom in. I'll just remember to zoom out when I have to show something in the code book. All right, there we go. And now here, just note that, again, this is why I change it, just to remind you, the voltages can change in the exam. Now, in the exam, we're only looking at single phase, so they'll either be 120 or 240, but notice this question 3, since you'll need it for question 4, is now 120 volt. Don't divide it by 240, just because we did the last one with 240.
It's a single phase, right?
Correct, that is single phase as well, which is implied. Good question. It is implied out of the 120. Good job.
Yeah. That was a good question.
You did great with the setup that I set up.
That's a question Dylan probably asked.
Except I haven't.
No. I don't ask if 120 is single phase. No, but that's something you should know.
Yeah.
That's something
We
you
should
should
be getting there. I wouldn't say it's something you should have memorized, but it's something we should be getting there already. And through code B, we should be getting more familiar with what's single phase voltages versus.
You might just want to drop the class.
So yeah, if you don't know this, then what? No, just kidding.
Just in common sense.
Yeah, go back to
I mean,
the-
I'll keep talking about voltage and referencing it. So we'll keep mentioning the 4. There's the 4. What are the 4? 120, 208, 240. Well, technically the 5. Sorry, 277, 480. Yeah, those are the 4. 5. Again, I said it. But so not many. Don't worry. It's not 30 of them to remember. It's only 5 of them. All right, I'm gonna start to bring that over here. So yes, single phase, so we're looking at 2 times. I keep everything in order, so 12.9 times the amperage now, which is 18. And my footage is 200. 12, smaller number, 6530. And then we'll have a number there. What do we have? What do you guys got?
14.22.
14.22. 22. All right, 14.22. I'll put it down here. So that is question 3, just to give us the correct letter that you're gonna. Again, you can have the numbers, but I'm making it easier here by showing you. So question 3 is C, 14.22. Very good. So we're losing 14, almost. Well, yeah, no, not almost 15. I guess we can land at 14 with that one. Off of 120, this gets us into what, 106? Probably no. But now how do we know percentage-wise where we're at, which is what question 4 is? We divide by the 120. Again, don't forget to move that decimal around. What is it? What do we got?
Yeah.
11.9 is what you guys are getting?
11.85 technically.
Okay.
Correct.
Yeah, that's rounded up.
Percent-wise. That's why I was like, but see, as you get more experience, do I have to do these? Well, sometimes you just look at the voltage number and go, nah. Like 106 is a number that I would not be comfortable with on a circuit that's going to be should be expecting 120 when they plug in. That's going to give me, remember what that does to the amperage. Once we drop to 106 volt, that's going to increase our amps. All right, and at 120 volt world, you might be dealing with a 15 amp breaker. You might be dealing with a small fuse. So this would be something that I would definitely adjust. I would run, instead of a number 12, which is what this circuit should get, I'd run a number 10 here.
Yeah.
There's a cutoff point. It should be 110, in fact. The cutoff point should be 110. All right. And so 11.9 is the correct answer as well. Very good. And that's going to be D. All right, so questions 1, 2, 3, and 4 you have the answers to. And so easy enough and practice for tomorrow, but also complete the assignment and get a grade, which is just complete the last 2. If you know how to do that, you're going to be comfortable going into tomorrow for the voltage drop question.
What's the multiplier for 3-phase again?
1.732.
What page is that on?
Idiot.
What page is that on in the or what?
Sorry, I was reading a question. Ask that one more time, but the question before that.
Oh, what's
210.
210.
What?
Sorry, what was the question before the last question?
For the 1.732, what page is that on?
Oh, 1.732. What page is that on the code book? I
Yes.
don't think it's in the code book.
Why?
It's in the
No.
Uglies book for sure,
Is that? What I told you.
but I don't think it's in the code book.
Oh, it was.
I just learned what.
Yeah, thank you. Just to address the online, thanks, Savannah. Yes, it is C. Michael, sorry about that.
Good when I say it.
Sorry about that.
I think right now you can.
Just in case question 4 was D. Sorry, 1.732 is not in the code book. It's in the calculator. It's just what the code book tells us is it's the square root of 3. I mean, it might be in there in a formula somewhere, because I know the code book throws formulas around. So right off the top of my head, I don't know.
I don't really
where it's at specifically, but I know that we do it because it is the calculated out number of the square root of 3.
So for three-phase, it would be 1.732 times the 12.9 and whatever is left.
Yes, times the copper times the. Now, if your question was where is this formula in the code book, then also there isn't this formula in the code book as well.
Okay.
Now, I do have the formulas posted. Now, remember, you don't need the three-phase one for tomorrow, but if you want the formulas at all, then I posted it here under the voltage drop formula sheet, and I'll open it up here. And of course, now it doesn't want it. There it is. It popped up right as I was clicking off of it. And I have both, right? So I have the single-phase formulas. It is the first two on the left. There's the voltage drop. There's the circular mills, using only the circular mills method. All right, we're only using that circular mills method, the one here on the left. We're not using this one on the right. And then you also have the three-phase one there as well. You have the full setup as well. Again, you can always calculate the length of the conductor using this. You can calculate the amperage using this. If you were missing one of them, with every formula, you have multiple ways to find each individual thing in the formula.
Right now, we're just focusing on VD.
Exactly. Right now, we're only focusing on the two on the top left. That is all tomorrow's exam is going to have.
Yeah, that's the most information.
Good. All right, so there's that completed. Don't forget to turn in the voltage drop. 2 people have already done that, so awesome. But you have just, in case you have till next week, Wednesday, but don't procrastinate. You only need 2 last ones. Okay. Going back. Okay, so that takes care of everything that I want to do with what's here. Now, I do have one last note here, but let's head over. Which, by the way, again, this conductor sizing and 31016 goes with our conductor selection as well there. All right, those two are partners there. But for table 3, the temperature correction factor, let me give you these notes instead that I have here, which puts the terminologies that we're talking about, adjusted ampacity, correction factor. This is what we did yesterday. This is the last bit of math that's going to be on our exam. And these are the 2 things that, these are not like steps or anything. This is, I don't even know why I numbered them. OCD probably. Just I need to structure it, but it's just random, right? They have nothing to do with each other. Adjusted ampacity, correction factor, and size the conductor, which again, as I said, I had here. Now give me one second. I'll be right back to this just to make sure. Okay, good. I have a question there. So for adjusted ampacity, I'm going to add stuff here. You guys go ahead and write, and I'm going to just start to put a couple of extra things down here. CF is just going to be correction factor.
Got some sea shanty stuck in the head.
Oh, sorry, this was conductor selection. Oops. There we go. Sorry about that. And I guess we don't need the or. Okay, so in this world of temperature correction factors and temperature adjustments. All right, going back sort of to the last note that was on the other page. I'll turn back to it a little bit later, but that was where we were going to do the temperature correction factor. And these were the two ways in which the questions were going to get asked. Either the adjusted ampacity or conductor selecting, dealing with a temperature correction factor. And so those are the two formulas for each. When you're adjusting the ampacity of a conductor, then you're going to multiply the ampacity of the conductor times the correction factor. And when we're trying to select a wire, the question will have the amps. That's what that amps is referring to, the ones that the question asks us to size the wire for. So those amps divided by the same correction factor that I mentioned. Now the table for those you had, those are the first, that's the first set of notes that I gave us, the tables. So we have the table for the correction factor, which again is 31015 B11, which I'm gonna go ahead to now. I'll have a page in a second. But I am not there yet. So hopefully I'm buying some time while you finish writing those notes. All right, there we go, I passed it. So. All right, I'm gonna just pop over to it. All right, this is the table here. So let me zoom back out so that I can square up the code book a little better. All right, this is the table, the 310B11. If you're using your code book right now, make sure you highlight this. Reason being is there's a table that looks a lot like it right below it. It's not for the conductors that we use. It would be for another set of conductors that I'll show us. These conductors are, we'll talk about them when we actually do this article, 310. But that's what these conductors are. They're, if you can see here, they're of a higher temperature rating. Where we stop at 90, these go up into 150, 200, and 250. Usually, these are going to be for things like motors or machinery and something like that, which we get into these. This is a higher temperature setting for the wires. So make note of that. If you see that 40, 140, that's not our table. We want the table that has the 30 degrees Celsius, 86 degrees Fahrenheit, that limits the conductor temperature to 90. All right, make sure you're using the right one.
Then, for this one, we have to determine whether what question is asking us for the temperature, right?
Yes, so let's look at example questions like that. Very good. We have to figure out which one the question is asking us to do, because one is multiply, one is divide. So I'm gonna make it as straightforward as I can. I don't know how or why anyone would want to confuse this, but I'm just gonna simply ask it. What is the adjusted ampacity of, and this should be blank here for a wire that I'm gonna give us. And then, I guess I wanted it over here. At an ambient temperature of a temperature that I'm gonna factor into the question. All right, and here I have the steps. Remember, I gave us the steps yesterday. You might already have them, but I have the steps here as well. All right, with the corresponding code tables. These are all tables. So let's throw in a set of numbers here. As always, these don't matter. It's any number will be fine. We just have to focus on, and that's why the first step is find the ampacity. So let's say we're dealing with number 4, THWN. So we're looking for the adjusted ampacity of this wire, dealing with a temperature of, let's go with 131 degrees Fahrenheit. That's a good high number. I'll be right back.
.67. Wait, what are we multiplying?
You forgot?
I forgot already.
To pay attention. All right, that was the answer, or they just like, yeah.
I'm still right.
Why are you writing it? It's written right there.
Because
I don't remember what to do. I know that I need the center column, that's all I know.
Alright, good, good. All right, and Savannah, if you or Michael, if you guys have the answers, you can type them in too. We'll walk through them.
Yes, it is center column. Excuse me.
All right.
How dare you disagree with me?
All right, so hopefully the steps were easy to follow or within some reason. Now, again, this one now we're not going to treat. The only thing I want to make sure is that you're not treating this one like any kind of specific column 60 or 75. We ignore all that, although there's no amperage to really take us into any of them. But we're looking for the insulation type, which we find in the 75-degree column. So again, remember out of step 1, 2 things we take note of. 1, the amperage from the wire, 85, number 4.
Oh, 95.
Number 4, 85. THW, not THW, or sorry, THWN, not THWN-2. No, not THWN-2, THWN. Alright, there's an easy slip on a question. Just wrong column, 2 different answers. See, we started 10 off. At the end of it, it might get you sort of close to the, well, no, not really. This one's just going to have a number at the end.
THW again.
Oh,
85. All right, that was our starting point, 85. Now we are multiplying it. We are losing. But here's what I said. The question's going to give us 2 bits of information. 1 was the 85. 2, where the insulation was found, which is what we need now. We take note of the 75 and we head over to the table, which places us in the correct column, the 75-degree column. And here is where we're getting our correction factor from. What was the temperature? 131? Oh, right at the end. I didn't know that. Last one, so 0.67, right? 0.67. I know.
6.7.
Is that still a thing? Is it? It's gotta end soon. Everything ends eventually. This one too. All right, 56.95. That should be the adjusted answer.
how'd you get the
Yo, pipe down, Michael.
Here's the question: how do we get the 85s? Right? We got the 85 because the number 4, THWN. When we go over to step 1, page 310, or sorry, table 31016, we find that number 4, THWN. Again, THWN is there.
Look to the right.
We come down to the number 4, and it's 85.
It's a wrong table, dude.
Highlighted the whole thing.
By the way, yeah, I'm not sure if this is what was being said, but there is another table here again. Make sure you're in the right table. There's another table that looks like it.
I was looking at the wrong one, that's why.
Yeah, no, here's the thing about table 31017. It looks the same. It has THWN, it has all of the, it is literally the same, except the amps are different because this is putting the wires in free air, no conduit. They're outside in free air. So notice what happens. They actually gain a little bit of amperage. That number 4 that we are saying is 85 amps. Look at it here. It's 125 amps. It can hold, what is that? A lot more amps. I don't know. You guys do the math. It can hold a lot more. 25 was that 15, 25?
But the wrong table was in reference to the ampacity one that you were very, very clear as to which one.
Okay, all right. Got it. All right, excellent. So just also when we make these mistakes, it's good now, as long as you know where, and oh, it's a no problem fix, but if it is a problem fix, then we'll deal with it here. Just make sure I got it. Yeah, I got another question, so make sure. All right, so again, the steps help us walk through the process. Our step one is find the ampacity of the conductor. And then step two is finding that correction factor. But these two go together. All right, we have to make sure that we're tying in the column that the wire was found on, and we're matching the temperature correctly. Oops, I was pointing at the wrong thing. Correction factor, that way. These numbers change depending on what column you're in. So focus on the columns. And yes, if the mistake was made over at the other table, as long as you know where and why, then we should be okay. I want to do one last one. It is 11:31 again. The same as with everything else. If you want to do any more practice questions after we're done, then hang out and we'll do them. But here's the last one in the world of temperature, which is what size conductor, sorry, I guess I erased wire when I was erasing wire. Well, actually, no. Blank, yeah. Is needed for, okay. So here, I'm going to just tell you THHN, THWN, sorry, I need a third one. THWN, so I'm going to place an insulation here. What size, let's do THHN. THHN conductor is needed for, here's you're going to get an amperage. Any amperage will do. We'll put a number here. Let's say we're dealing with 200 amps. All right, so we have an insulation that we have to go and size this wire to, an amperage that we have to size that insulation type to, and then we're going to be dealing with a temperature the same as the last one. Now I'm going to throw in a Celsius. I just don't have those memorized, so I want to make sure it's one that I can use, and we'll go with 47 degrees Celsius. Yeah, that one's better. So here are the steps for that one. By the way, I didn't reference that here. Yeah, this one was, I didn't give us this yesterday. I implied it yesterday, so I'm putting it here just to better prepare for the exam. Now, again, remember what I was saying yesterday. If you know what temperature rating THHN is, which that's one to memorize, then you don't even have to go and do the step one that I have here. Saves you on that.
Is it a 4-aught wire?
I don't know, but it sounds like it probably will be.
I found 3.
We got a 3-aught. All right. We're battling it out. One person 3-aught. Now here's the thing. The 3-aught person, if they send me that bill or that bid, I'm going to think that's going to be a cheaper bid. So will I go with the 3-aught person? But here's where I make if they're wrong in their calculation, they eat that cost. If the inspector comes and goes, hey, this is supposed to be 4-aught. They eat that cost. So
What do you mean?
I pay less and they pay more. So here's where we want to make sure our wires are sized correctly. But I don't know. So again, if you need step one, you need step one. If you don't need step one and you already know that THHN is a 90-degree conductor, then you can just go and start step two, which is why I put step two yesterday as our step one, since we were more lecturing about it. All right, so now it places me where my correction factor is found. And now I just look at the temperature, which is 47 degrees Celsius, right there between 46 and 50. My correction factor is 0.82. There we go. So if you got that, you started off good. So far so good. If you didn't get that,
Why is it at the 90 degree vacuum?
why is it at the 90 degree?
Because it on here.
This one right here.
Yeah, exactly. So these are all 90, these are all 75.
Remember, the reason why we're at the 90 is right there.
Never mind.
Okay. Okay. Sorry, maybe that was not what you were asking, but
No, I put down a W instead of an N.
okay. So divide now, right? Divide the amps by that. So again, which amps? It's in the question, so nothing else is needed for there. And remember, we're going one size higher. So let's see if my contractor who bid the 3-aught and gave me a cheaper price that I chose to be my contractor has led me into the correct direction. And we're not gonna fail this inspection. And then they're gonna walk off the job site. I gotta go sue them. All right, where are we looking for this wire from, or which column? Remember, now it doesn't have anything to do with 60 or 75 degree. We are being told the wire must come from the THHN column, meaning the 90 degree column.
The wire.
So if we're trying to find 243.9, 244, then that failed that inspection.
Yeah, you guys failed that inspection.
It is the 4-aught.
It's okay, Luis, we both know.
So
Yes, before doing the work.
No, I did all the work before you,
not 4-aught. All right, look, I'm gonna stop this video here.